welcome to lecture 6 in the series of videos on statistics. Currently, we are in the series of statistics for CFA and FRM level 1, but these series of statistics will also help you in developing your basics around machine learning, data science, and definitely actuarial science. In the series of lectures, currently we are into descriptive statistics. In the last 5 lectures, we covered moment 1, moment 2, moment 3, and today we'll cover moment 4. If you remember, moments were only or descriptive statistics is to describe or it's about describing the look and feel of the data. So whatever we'll discuss today is to be discussed and to be understood from the perspective of what is the look and feel of the data. And today, specifically, we'll talk about whether the data is fat or thin. In moment 4, you have to understand 4 things. First, what is the fatness or the thinness in the data, and specifically whether the data has the fatter or thinner tails, not body, tails. Second, you have to understand that moment 4 is measured with the help of kurtosis. Then you have to understand the terminology like mesokurtic, platykurtic, and leptokurtic. And the last, you have to understand excess kurtosis. These 4 things. And that is what we'll discuss in this lecture. As I mentioned, that moment 4 is all about fatter or thinner tails in the data, not body. Now, fatter and thinner are relative word, or even when you say someone is fat or someone is thin or someone is physically fit, it depends how you perceive fitness. It is a relative exercise done by your subconscious mind. Even a society subconsciously label people with fat, thin, or fit, and it depends upon that how society perceive that person, right? So it's a game of perception and it is a relative perception. The same way in the society of data, we have to decide what is fatter, what is thinner, and what is a fit data. So unanimously, the society of data, as in all the statisticians decided, the fittest of all is one distribution, that is normal distribution. And this is how it looks. Now we don't know what is normal distribution, but we have to discuss normal distribution and inferential statistics when we start probability distribution. So we haven't started probability and probability distribution, but don't worry. We are just trying to understand moment 4 from the perspective of look and feel, descriptive statistics. So what I'm saying, normal distribution is the fittest of all. And why it has been decided fittest of all? It has been decided fittest of all because it is being considered as a God distribution. And why it is a God distribution? So there is a video in this channel, Sofer channel, on normal distribution. Why this distribution is everywhere and why this distribution is considered as a God distribution. So because by statistician, a feeling is this is a God distribution, they said, okay, normal distribution is going to be the fittest of all. So if I have to compare whether a distribution has a fatter or thinner tail, I'll compare with the normal distribution, and normal distribution is the fittest distribution. So again, this curve is normal distributed or normally distributed curve. And I have a distribution, which is this distribution. It was given to me. What I'll do, I will put this distribution on normal distribution and try to compare the tails only. If it has a fatter tail, and you see this has a fatter tails. This is the body, this is the tails, it has a fatter tails. And if it has a fatter tail, I'll say this distribution is a leptokurtic distribution. What distribution? Leptokurtic distribution or leptokurtic data. Fatter. Again, if I got a distribution and this is my normal distribution, again I got a new distribution. What I'll do, I'll put that distribution on normal distribution. So this is the distribution, the new distribution that I got. And this distribution has a thinner tail than normal distribution. I'll call it as a platykurtic distribution. That's it. If it has a fatter tail than normal distribution, we'll call it as leptokurtic distribution. If it has a thinner tail than normal distribution, I'll call it as a platykurtic distribution. If by chance you get a distribution which has equal tails, fatness or thinness, or equal tails as normal distribution, I'll call it as mesocurtic distribution. So normal distribution is also called as mesocurtic distribution. So mesocurtic, the thinness of fatness of the tail equal to normal distribution, or normal distribution can also be called as mesocurtic distribution. If it has a fatter tail, leptocurtic distribution. If it has a thinner tail than normal distribution, then a platykurtic distribution. Perfect. Now, the way we measure it is the way you measure, mathematically you measure. There should be a formula to measure this fatness or thinness. The formula is of kurtosis, is kurtosis. And that's why we were calling it kurtic. Mesocurtic, platykurtic, leptocurtic. So kurtosis. Let's discuss this formula, first of all, in the terms of relativeness to other moments. Now, in moment one, the formula for mean, which was the center, was summation of xi upon n. The power was 1. This was the mean formula. For moment 2, this was a variance formula. The formula was summation of xi minus mean raised to the power 2 upon n. This was a formula for variance. Okay? Moment 2, power 2. When we discuss moment 3, which was skewness, in the last session we discussed skewness, then we did xi minus mu raised to the power 3 summation divided by n, and then what we did, we divided by standard deviation cube to make it unitless. What we are discussing right now, we are discussing moment 4. So definitely, if I talk about the pattern should be summation of xi minus mu raised to the power 4 upon n. And again, understand it is about fatness or thinness in the data. So we don't want any unit. It should be unitless. And therefore, we divide it by standard deviation raised to the power 4 of the data to make it unitless. This is the formula of kurtosis. Now, this kurtosis will throw certain numbers. Now, if it is a mesocurtic distribution, or actually if it is going to be a normally distributed distribution or data, then the kurtosis will always throw a number 3. It's not any magic, because the normal distribution probability density function we all know is 1 upon root 2 pi and e to the power minus x square by 2. This is the general PDF of normal distribution. Assuming the mean is 0 and standard deviation is 1, if you do the integration and do this maths or summation or whatever you want to do, every time the kurtosis is going to be 3 because the PDF is defined. So if the kurtosis is 3 for a mesocurtic distribution or normal distribution, how would you compare mathematically if you don't have these distribution plotting provided to you? Only you got the kurtosis number. How would you know it is a platykurtic, leptocurtic? You just compare with 3. That's it. If the kurtosis is greater than 3, then kurtosis minus 3, which is the excess kurtosis, will give you a positive number. So it is going to be a leptocurtic distribution. If I got a distribution and the kurtosis is actually less than 3, then this is excess kurtosis, which will give me a negative number, and that is going to be a platykurtic distribution. So we discussed about what is the look and feel of moment 4. We discussed about how you measure moment 4, but we haven't discussed one important point. What is the mathematical inference of the data? The mathematical inference of the data, it is slightly difficult to discuss this mathematical inference because we haven't discussed probability and probability distribution. So assume this is a normal distribution, and this is the center of the normal distribution. At this center, what we'll have mean, median, and mode. Then what we have in the left direction and the right direction is called as outlier, because it would be positive, infinity, it would be negative infinity. So these are called as outlier. And the height of these plotting or these distribution talks about probability. So at the center, the height is maximum, it means it has the maximum probability. So height determine the probability. This statement is not 100% correct, but for the timing, assume the height of a probability distribution gives you probability. So when I'm talking about a distribution which has a fatter tail, it means the probability of outlier where the distribution has a fatter tail is higher than the probability if it would have been a normally distributed data. So it simply means that the probability of outlier in leptokurtic distribution, which has a fatter tail, will have a higher probability than normally distributed data. If it has a thinner one, then the probability of outlier is going to be lesser than the probability of outlier in a normally distributed data set. And that is what is the inference or the meaning of fatter tail or thinner tail. If it has a fatter tail, it has a higher probability of outlier in the data. If it has a thinner tail, it has a lower probability of outlier in the data. If you want to connect it to economics, if it is a developed country and assume the developed country, the positive return and the negative return of the stock price are, or the returns of the stock price is normally distributed. But if it is a developing country, then the probability of extreme positive and extreme negative return is higher than the developed country. So definitely when you plot the returns of a developing country, it is going to have fatter tails because the probability of extreme outcome or the probability of outlier is going to be higher than the probability of extreme outcome or extreme positive and negative returns coming in a developed country, right? So higher probability of outliers. Okay. With that, we have covered everything in moments. We have completed moment 1, moment 2, moment 3, moment 4, and soon we can enter into the interesting stuff that is inferential statistics. With that, I'll end the session here. Thank you. Have a nice day.